Most students think kinematics is about memorizing 4 equations, but the harder part is knowing which equation to use when. Here we have a car starting from rest. It accelerates at 3 meters per second squared for 4 seconds. And we want to find the final velocity and the displacement. By the end of this lesson, you'll know how to choose the correct kinematics equation and solve problems like this step by step. There are 5 key variables for kinematics. Delta x, the delta is the Greek letter here, which just represents a change in x, is displacement measured in meters. Acceleration, denoted by a, is measured in meters per second squared. Time, denoted by t, is measured in seconds. And then both initial velocity and final velocity are measured in meters per second. So I've written here each of the 4 kinematic equations. We're going to go into each of these in more detail, but I wanted to get these all up right away. If you have some familiarity with these equations and you're looking for more practice problems and delving into each of them individually, you can go ahead and skip to the timestamps in the video. But we have final velocity equals initial velocity plus acceleration times time. Displacement equals initial velocity times time plus 1/2 acceleration times time squared. Final velocity squared equals initial velocity squared plus 2 acceleration times displacement. And then finally, displacement equals 1/2, and then in parentheses, final velocity plus initial velocity times time. 2 important notes. These equations only work for constant acceleration. If you have a problem with changing acceleration, then these equations will not work. But I don't think that you'll be likely to encounter changing acceleration problems, especially not this early in Physics 1. And then one other side note, these mean exactly the same thing. So you have initial velocity is sometimes denoted instead of v sub I, it's denoted as v naught. So a little 0 in the bottom. And then this is initial position or initial x value, and sometimes it is also denoted as x naught. For the purposes of these videos and the remainder of this video, I will be using v sub I and x sub I to denote initial velocity and initial position. Let's look at the first equation here. We have final velocity equals initial velocity plus acceleration times time. And we're going back to the problem that I started with at the beginning of the video. Each of the 4 kinematic equations has 4 of the 5 kinematic variables. So in this case, we have final velocity, write them down, initial velocity, acceleration, and a time. We are missing delta x, or displacement. So this equation is useful when we know these 4 variables, or 3 of these 4 variables, but we don't know, or it's not necessary to know this one. So let's go ahead and solve this problem. To restate it, we have a cart accelerating at 3 meters per second squared for 4 seconds. So we know acceleration, it is 3 meters per second squared, and our time is 4 seconds. This cart specifically, I should have mentioned, is starting from rest. When an object starts from rest, it means that its initial velocity, forgot I wrote it over here, is 0 meters per second. It doesn't have any initial velocity. So we can plug these 3 variables now into our equation, and we get that final velocity equals 0 plus 3 times 4, which just equals 12 meters per second. There's one other important thing I want to point out here. Let's give ourselves some space to calculate. And let's say that in this example, we actually don't know the initial velocity. It's an unknown. But we do know the final velocity, the acceleration, and the time. We can rearrange our equation to solve for the initial velocity with some simple algebra. So instead of having final velocity equals initial velocity plus acceleration times time, we can subtract acceleration and time from both sides. And we end up with final velocity minus acceleration times time equals our initial velocity. If we use the same variables from earlier, we end up with 12 meters per second as our final velocity minus 3 times 4, which is 12 minus 12, and we get the initial velocity of meters per second. With a little bit of algebra, you can rearrange this to solve for any one of these 4 variables. If you know final velocity, initial velocity, and acceleration, you can rearrange it to solve for time. Similarly, you can rearrange to solve for acceleration, and this is true for any of the kinematic equations. And I'll try and show some more examples of that as we delve into each of the equations. Here's an example problem dealing with equation number 2. Equation 2 is missing the final velocity. That's the term that is not in the equation, but it has displacement, initial velocity, time in 2 separate places, and acceleration. This first term represents the distance that the object travels based solely on initial velocity. And the second term represents the distance that the object travels based on the acceleration. I've also written this in the form of a word problem here, so we can practice with taking a word problem and turning it into an equation. I'm going to read through it and I'm going to highlight the things that I find important. We have a cart starting with a velocity of 2 meters per second. And it says it is starting with that. So that's our initial velocity right there. Initial velocity equals 2 meters per second. Then we have that the cart accelerates at 4 meters per second squared. So we have our acceleration. And it says that it does this for 3 seconds. So we have our time. Finally, it asks us to find the displacement, which shows us what we want. Once you've written all these out, if you have the kinematic equation memorized, you can easily see that equation 2 is the one that applies. So we can take all of these variables and plug them into equation 2. So delta x now equals 2 meters per second for the initial velocity times 3 seconds for the time plus 1/2 4 meters per second squared for the acceleration, and then 3 seconds squared for the time. If you calculate all this out, we end up with 6 plus 1/2 times 4 times 9, and this will equal 24 meters as our displacement. Let's go over equation 3. We have final velocity, initial velocity, acceleration, and displacement. The problem I've written is that a car slows to a stop at a rate of 4 meters per second squared. We can see it's 4 meters per second squared, and so that is the units for acceleration. So acceleration, 4 meters per second squared. Over a distance of 8 meters. We have distance, so we have delta x, our displacement. What was the initial velocity? So we know that we want to find the initial velocity. We're missing one thing though. Let's read through it again. A car slows to a stop. Okay, that is something that may be tricky in some physics problems. We see that it's slowing to a stop, so that tells us that the final velocity is equal to 0 meters per second. Similar to how if it said it's starting from rest, we know that the initial velocity is 0 meters per second. So now we know we want initial velocity. We have final velocity, acceleration, and displacement. So this equation works. Let's rewrite this equation to solve for initial velocity. We have final velocity squared equals initial velocity squared plus 2a delta x. Let's subtract this from both sides. so that we end up with initial velocity squared equals final velocity squared minus 2a delta x. And then we can take the square root of both sides to get rid of the 2 there. We have initial velocity is equal to the square root of final velocity squared minus 2a delta x. It's only at this point that I've solved the equation symbolically that I plug in my actual values. If you plug them in from the beginning, you may find it messy, especially if you're dealing with decimals or fractions. So we can say for this problem, we have the square root of final velocity is 0 minus 2. Acceleration I put as 4 meters per second squared. However, this isn't entirely accurate, and I did this on purpose so I could point it out later. The car is slowing down, and so we know that the acceleration is actually negative. It is a deceleration. So it's 2 times negative 4 times delta x, which is 8. So we have initial velocity is equal to the square root of negative 2 times negative 4 times 8, which is 64. Square root of 64 is 8, and the units are meters per second. Let's go over the last equation, equation 4. We have displacement, final velocity, initial velocity, and time. And we are missing acceleration. Come up with a word problem here. We have a person walking with a velocity of 1 meters per second. So that is our initial velocity. So 1 meters per second. They speed up to a velocity of 3 meters per second. So that's our final velocity. Over a time of 3 seconds. So that is our time. And it asks us how far did they travel? So it wants delta x. Now the reason I used a person instead of the cart is I wanted to draw this out. It's really helpful to draw out the physics problems that you encounter. So we have here our little stick figure person, and they're moving with an initial velocity of 1 meters per second. And we know that over here at some point, they have a final velocity of 3 meters per second. And that the time it takes them to do this is 3 seconds. We can define this direction to be positive, and we know that we want delta x in the middle, their displacement. It may seem unnecessary to draw it out for an equation like this, or for a problem like this, but getting practice with drawing out your physics problems is really helpful and will really, really set you apart from everybody else as you progress through your physics courses. If you're able to look at a problem and break it down into what you have, what you need, and draw a picture, you will get probably 50% of the points right there on any question you encounter on any exam. So let's go ahead and calculate this. We have delta x equals 1/2 final velocity, which is 3 meters per second, plus initial velocity, which is 1 meters per second, times time, which is 3 seconds. So this is 1/2 times 4 meters per second times 3 seconds, which equals 4 times 3 is 12 divided by 2. 6 meters is our displacement. We can go ahead and put that here. Thank you guys for watching to this point in the video. I now have another example problem for you guys to try on your own. I've listed the 4 kinematic problems here, and I've also listed the steps to solving any kinematic problem to help you guys out. Go ahead and pause the video now and give it a try. All right. We have a ball that is dropped, not thrown. That's important. That tells us we have some initial velocity of 0 meters per second, from a 10-meter building. Well, that's important. We have a 10-meter building, so we have some sort of delta x, 10 meters. Given that the acceleration due to gravity is 9.8 meters per second squared, so we have an acceleration. How long does it take to reach the ground? So that is our desired value, our time. Make a little bit of space here. So I've listed all of our known variables, and I've also identified the unknown variable. So now we just choose the equation containing all of these variables. We need initial velocity, acceleration, and displacement. The first equation isn't it because we have a final velocity, so we don't need that one. Next one isn't it, also because we have final velocity, and the same with this one. And we're left with this equation as the only one that satisfies all of our needs. So all we need to do now is solve this equation for time. I'm going to move it over here to give us some space. And then the first thing I'm going to do, this is just a little trick, is we notice that the initial velocity is 0 meters per second. So if we plug that in here, this whole term cancels, leaving us with just delta x equals 1/2 at squared. We rearrange to solve for t, and you end up with t equals 2 delta x divided by a. You take the square root of that. We plug in our values to get square root of 2 times 10 meters divided by 9.8 meters per second squared. And if you plug this into the calculator, you get an answer of roughly, let me see, 1.43 seconds. This practice problem was a little bit of a teaser into the next video where we'll apply all of the equations to free fall and vertical motion under gravity. Thank you again for watching. Please don't forget to like and subscribe if this helped you out.